Okay, now that we've looked at some normal curves, let's look at how we would expect to find data among a sample in comparison to the normal curve. And one way we'll do this is by looking at standardized scores, also known as z-scores. What a z-score tells you is how far above or below the average you are in terms of standard deviations. So notice what z is defined to be. It's the distance of my measurement versus the average divided by the standard deviation. So the z-score literally tells you how far above or below the average you are in terms of standard deviations. If your z-score is 0, it implies that your score matched the average population. If it's positive 1, you're 1 above. You're 1 standard deviation above the population mean. Negative 1, you're 1 standard deviation below the population mean. If you're positive 2, you're 2 standard deviations above the population mean. That's pretty rare. Similarly, if your z-score is negative 2, you're 2 standard deviations below the population mean. And that too is relatively rare. You can have any kind of z-score ranging from negative infinity to a positive infinity. One way we'll use z-scores is trying to figure out how a measurement is different or compares to the population measurement. Is it similar to a population measurement or different? If the z-score is positive 2 or positive 3 of a sample, that would imply that you're 2 to 3 standard deviations away from the population mean. It's not very often you find sample measurements 2 to 3 standard deviations above the population mean. That could be because you're an outlier, could be because you made a bad measurement, or it could be because you've truly found a different segment or group of respondents that are truly different in some dimension. An example of z-scores is often used with IQ scores. The average IQ score was designed to be at 100, and the population standard deviation is 15. Thus, an IQ of 110 is above average. Yes, it is. However, its z-score is 0.67, so it's still within a single standard deviation of the mean. And in some ways, you would say, well, that's pretty much average. Likewise, an IQ of 95 might seem below average, but if the z-score is only negative 0.33, it's still within a standard deviation of the mean, and so therefore I would say it's still somewhat average. It's not until you get an IQ of around 115 that you start to finally get above average, really above average. That would imply you're 1 standard deviation above average. To get an IQ of 132, you'd be 2.13 standard deviations above the average. That person would qualify to join Mensa and has a truly unique intelligence. Similarly, an IQ of 69 has a z-score of negative 2.1 and is significantly lower than the average by more than 2 standard deviations. And such a person is often qualified as a special needs individual by most U.S. governmental agencies. To interpret z-scores in general, you would simply state that a z-score of 1 or negative 1 lies within a standard deviation of the mean. 2 lies within 2 standard deviations of the mean. And outside of 2, you would say that that is definitely unique. If it's positive 3 or negative 3 or positive 2.1 or negative 2.7, it's definitely unique. It's definitely outside of the expectation range. With z-scores, we can express the standard normal curve with this very simple equation. Notice that in this equation, 1 over the square root of 2 pi e to the negative z squared over 2. There is no such thing as an x bar or a mu or a sigma or an s or anything of that nature. Why? because it's all been included in this term Z, where Z is simply the difference of my measurement from the population average measurement divided by the standard deviation of the population. To get the standard normal curve distribution in Excel, simply use that norm dist function once again to set the mean at 0, the standard deviation to be 1, and again use the false. So we'll end up with the standard normal distribution. This leads us directly into the idea of confidence intervals. What a confidence interval does is it defines a range of values in which you would expect to find a measurement. Z-scores, say I measured a Z of 2. And we said that that seems unreasonable or unlikely. Well, what's going on here is I'm actually mentally already comparing it to a confidence interval. For instance, consider a measurement of the population mean and standard deviation. So you know the population mean, mu, and you know the population standard deviation, sigma. Then you go out there and you find a sample. So if you took a measurement of a sample, calculated that sample's arithmetic mean, x bar, the confidence interval defines the likely range in which that sample's arithmetic mean will be found. Got it? I'll show you in a second. If that sample deviation, if that sample average, so you're comparing x bar to the population mean, mu, using now standard deviation. If that sample is not found within that confidence interval, where the confidence interval will also require my standard deviation. So once again, if that sample is not found within the confidence interval, it is possible that the sample is not a part of the population. Perhaps it represents a different population, which indicates a different market segment. In contrast, if a sample is found within the confidence interval, it is probable that the sample is a part of the population, and it represents simply a normal part of the population, and it's just part of the overall market being served. Here's an example of confidence intervals. There's the 68% confidence interval. It goes from -1 to +1 standard deviation here. This covers that range. It's the probability that I will find a measurement here, or here, or here, or here, or here, or here, or here. It's the probability I'll find a measurement. 68% of the time, when I'll grab a sample from a population and I'll do a measurement, I'm going to find that measurement somewhere in this range. 68% of the time, it will lie within 1 standard deviation of the population mean. Now, 95% of the time, it'll lie within 1.96 standard deviations, which is almost 2. It's just short of 2. So 95% of the time, it's going to lie between -1.96 Z and +1.96 Z of my standard score. So now we're looking at our confidence intervals, and you're seeing how that confidence interval basically says, where do I expect to find a measurement? I'll give you an example. Suppose I'm measuring heights of individuals, and overall I know the average height of a female in the U.S. Let's say it's 5.4, 5 feet 4 inches. And then I'll go to some town, for instance, Atlanta. And in Atlanta, I measure the height of women there in that sample. And I measure their height not to be 5 feet 4 inches, but 5 feet 5 inches. I might want to say, well, is that really higher than the average, or is that within expectations? Well, I'd find the overall population standard deviation, I'd find a z-score, and I'd try to figure out if it landed within here or way out here. Now, if it landed way out here, outside of the 95% confidence interval, I might say the Atlanta women are slightly taller than the average American women. Again, this is simply a hypothetical. Here's some example confidence intervals that we can use. We have the 38% confidence interval. It's used sometimes, rarely, but it is used. And that is the probability. It is the confidence interval defined by a half a standard deviation of the mean. So it could be a half a standard deviation above. It takes the range of a half a standard deviation below to a half a standard deviation above. The probability that you'll find a sample mean within a half standard deviation of the population mean is 38%. So often you'll find a sample mean outside of a half standard deviation of the mean. Within a standard deviation of the mean is the 68% confidence interval. So 68% of the time you're going to find a measurement within one standard deviation of the mean. 32% of the time it won't. That is defined by the range of mu less a sigma up to mu plus a sigma. The 90% confidence interval is used quite often. So this is the probability you're going to find the sample measurement within the mean. At the 90% of the time, you're going to find the sample measurement within this range of the mean. And that is defined as the range of mu less 1.65 sigma up to mu plus 1.65 sigma. You're going to need to know these numbers like 1.65. Honestly, you will. It'll make your life easier. Roughly 2 standard deviations of the mean is the 95% confidence interval. The exact number is 1.96. So this is mu minus 1.96 to mu 1 plus 1.96. Within that range, within that interval, 95% of the time, I will find my sample measurements. 99% of the time, my 99% confidence interval is defined by the range of mu minus 2.58 sigma up to 2.5 mu plus 2.58 sigma, where sigma is my standard deviation. So 99% of the time, I will find a measurement of a sample within plus or minus 2.58 standard deviations of my population mean. What if I find a measurement outside of that range of a sample, like at the range of mu plus 4.8 sigma? Well, 99% of the time, I wouldn't expect to see that. In which case, I would say that it fell outside of the confidence interval, and I can suspect that that particular sample measurement is not like the others. It's of something else. And perhaps the sample is not representative of the population. Perhaps that sample is truly unique. Other handy numbers to know: probability of anywhere below the mean, or from negative infinity up to mu, the average, mean, is 50%. Of course, half the time I'm below the average, and half the time I'm above the average. 50% of the time I'm between the average and positive infinity. I mean, the average is the average. On a normal distribution, half the time you're going to be below the arithmetic average, half the time you'll be above it. Pretty clear. The probability of finding it between the mean and one standard deviation above the mean is 34%, which is exactly half of 68%, or the 68% confidence interval defined by mu plus or minus a standard deviation. Below one standard deviation above the mean, so from negative infinity all the way up to one standard deviation above the mean, covers 85% of the measurements. Why would we use something like this? Suppose we wanted to get the top 90%. The top 90%, the bottom 90%. The bottom 90% lies within the range of negative infinity up to 1.28 standard deviations above the mean. So 90% of your measurements are going to be below 1.28 standard deviations of the mean. That means 10% of your standard measurements would be 1.28 standard deviations above the mean or higher. That would be your top 10 percentile. Your top 5% will be 1.65 standard deviations above the mean to infinity. Notice that this number closely matches what we have here for our 90th percentile. Our top 2 percentile, that is 2 That is the average plus 2.06 standard deviations, all the way up to infinity. That is our top 2 percentile. And our top 1% of measurements would be 2.33 standard deviations above the mean, all the way up to possibly infinity. That is the top 1 percentile, top 1% of measurements. We can put our z-scores and compare them to our confidence intervals. So here we have the normal distribution, beautiful looking bell curve, or that Gaussian curve. And if you have a z-score of negative 1.8, you're down here. You can just plot it right there on there. You have a z-score of 0.9, you can just plot that. You say you're 0.9 above the average here. When I measure a z-score of out here, somewhere out here, or somewhere out here, I'm going to definitely say that that is not commonly found. It's relatively rare to find it. I might call that a different market group. When dealing with outliers, there's an important aspect to remember that if I measured something not just in here, but perhaps all the way out here, then we would have definitely an outlier. Sometimes this outlier indicates a bad piece of data, and it's time to just discard it. Other times, it indicates that perhaps my distribution is not normally distributed. Perhaps it is skewed. At other times, here's my outlier again. At other times, what it's measuring is that perhaps I have a different sample, one out here compared to my basic sample there. So it could imply a truly interesting and unique market segment. Which one does the outlier imply? Well, that might require more insight to where that piece of data came from. The next thing I want to look at is standard errors of sample measures and the confidence intervals. So now I'm going to put all of these parts together so we can begin to start looking at measurements and say, is it like the average part of the population, or is this measurement definitely unique? Now, to determine if a sample measure is within expectations of a representative sample of the population, we do the following steps. We first calculate the standard error of the measure. The standard error, denoted by SE, of a measure is simply equal to the standard deviation of the population divided by the square root of the number of people or the number of responses within my sample. So this is the standard deviation of the population, and this is the number of responses within my sample. The standard error is my population standard deviation divided by the square root of the number of responses within my sample. This is where I came from in saying that if I had a population of 1,000, my standard error is plus or minus 3%. One can derive such a generalized conclusion in many cases. After we have calculated our standard error of a measure here, using this simple formula, we then determine the confidence we wish to use. We usually will use the 95% confidence level. So we're going to go ahead and assume we're using the 95% confidence level. We can calculate the confidence interval to be that measurement we have of our sample, so this is our sample average, x bar, plus or minus 1.96 standard errors. Where did that 1.96 come from? Here. Let me erase everything on this. We have the 95% confidence interval defined right there. And it says I need the range from the average less 1.96 standard deviations to plus 1.96 standard deviations. So I'll take my confidence interval to be my measurement that I have of my sample plus or minus 1.96 standard errors. I'm now going to compare this 95% confidence interval of the sample mean to the population mean. If the population mean lies within the confidence interval, the sample is representative of the population. If the population mean lies outside the confidence interval, the sample is not representative of the population. Let me show you an example of that in Excel. Okay, so here I have a blank worksheet in Excel. I'm going to make the cells a little bit bigger and make this one a little bit wider as well. Suppose, as I have on page 80 of our workbook, I'm told a consider a sample of 25 measurements. So N equals 25, and a mean measure of 2.5. So our sample average is 2.45. That's what it says. When compared to a population mean of 2.3 and a population standard deviation of 0.5. So given this stuff, I can first find my standard error of my measurement. That would be my population standard deviation divided by the square root of the number of measurements within my sample, 25. So my standard error of any measurement is plus or minus 0.1. Next, I choose a confidence interval. I'm going to choose 95%. That would imply I'm going 1.96 standard deviations above or below the mean. So upper limit of my confidence interval would be my sample average plus plus my standard error times 1.96 standard deviations. And my lower limit of my confidence interval, so this is my confidence interval, would equal my sample average minus 1.96 times my standard error. There we have it. Making sure I grabbed the right stuff. I did. So here's my upper and lower limit. Final step is I look at my population mean, 2.3, and I compare it to this range. And is 2.3 within my upper and lower limit of my confidence interval, my 95% confidence interval? Well, 2.3 is between 2.2 and 2.6. So it is within expectations, or part of the overall population. Both of these would be making a similar claim. Since we're here, let's see what would happen if I had a smaller sample, like only 5 people in the sample. Notice that my upper and lower limit got larger. I'm going to try even a smaller sample, like 2. See, my upper limit, my range, my interval got larger. Here's 1, very wide. I'm going to go ahead and lock this down so it doesn't keep changing the sizes. There we have it. That'll do it. Now let's go back up to 25, which is what we had in the book. Suppose I had a very large sample, like 1,000, 10,000. Now I get a very narrow confidence interval, and if I compare my population mean, it won't fit within it. So basically, as I get a larger sample size, my confidence interval decreases. A small sample size, my confidence interval increases. So the more data I have, the more certain I am that my measurement is actually a measurement of my particular sample. The easier it is for me to determine if that sample is or is not like my population. The very small sample size, I'll have a very broad confidence interval. The very large confidence size, sample size, I'll have a very narrow confidence interval. Having discussed these aspects, you should be prepared to execute the exercises called paper manufacturing, FIFA, Viva España, Radiohead, Leo Burnett, and, Making the Bacon, All Souls Gather.